we are in chapter 13 and sections 1 through 6, and this is problem number 14. Well, my drawing is not very accurate this time because it's kind of complicated to draw a Formula 1 car, but you can look at the picture and the slide and what we say. So if we read, the car are traveling around a curve of radius 400 meters at a constant speed of 200 kilometers per hour. And they have a mass of 600 kilograms. And we can neglect the size, so we will treat the car as a particle. So we want to find how much is this angle so that we can neglect the friction. So you can imagine that this car, due to the slope, it will drag down because of the gravity, right? Or because of the speed, its normal acceleration will go up. So how much does this angle has to be in order to be able to neglect that friction? So we will not consider the friction in order to have the car stable in its place. So we will do the solution, right? For the solution, we always start with our free body diagram of the car. So I will draw just a little square, neglecting the size of the car. And what do I have? I have my normal force. So this is inclined, right? We know that this inclined theta, and we have the weight, right? So if that angle is theta, this angle is theta as well, right? And then if we draw our kinetic diagram, important part in this problem is to analyze which kind of coordinates we will use. So as you see, we are moving in a circular path. So if we look that from the top, we can imagine these cars traveling in a circular path. So this is my car, one of them, right? So they will have a normal acceleration and a tangent acceleration. Since the velocity is constant, you remember that the tangent acceleration is the derivative of the velocity. So since it's a constant velocity, that derivative will be equals to 0. But we still have a normal acceleration, which you remember is the velocity squared over the radius of curvature. And we are given the radius of curvature, this one right here, and they tell us that is 400 meters. Okay, so from the top we look at like that. From this view, then we have that this is our normal direction, and the tangent will be in this direction, and then we have B, right? So this is the normal, the tangent, and our vertical direction. So in the kinetic diagram, we draw our same particle, and then so we have the forces here, we have the normal force and the weight, right? And remember that what usually we would have to draw our friction force, that we don't actually know if the car is going down because of the gravity or up because of the acceleration, but we don't need to draw the friction because that's what they are asking us. What is this angle? So that we don't have to take into consideration the friction. So we have these two forces in our free body diagram, and then we have only normal acceleration. So our kinetic force is mass times velocity squared over radius of curvature. So now that we have our free body diagram and our kinetic diagram, we know that the free body diagram is equals to the kinetic diagram because my forces are equals to mass times acceleration. And this equation is a vectorial, right? So equations of motion. Those are my equations of motion. So I will add forces in my normal direction. What do I have in my normal direction? The weight does not contribute, but the normal force does. So it will be a normal force sine of theta, and I don't have any other force, will be equals to my mass velocity squared over radius of curvature. And then I have in the tangent direction, as you see, I have 0 here and I don't have any force, so it's 0 equals 0. but I just write it to have it, right? And then I have in my vertical direction, I have negative weight and positive normal for cosine of theta equals 0. First of all, well, our velocity is given in kilometers per hour. We have to convert that to meters over second. You remember, well, we have to multiply by 10 to the cube divided by 360. And I have done that calculation, and it's 55. So my velocity is actually 55.555 meters over second. So I have that velocity, I have the mass, I have the, so what I have to find is the angle. So what I'm going to do here, my normal force cosine of theta is equals to the weight. Being the weight, you remember, mass times gravity. So this is my first equation. This is my second equation. As you see, the sine and cosine, what I'm going to do is divide those two equations. I'm going to say that n sine of theta, so n cosine of theta, and in this side I have m velocity squared over radius of curvature, and divided by m gravity. So as you see here, n cancels out and m cancels out. So finally I have that, so theta will be the inverse tangent function of velocity squared over rho times gravity. So and that's the result. We obviously can plug in the numbers for rho equals 400 meters and velocity equals 55.5 meters over second, and gravity equals 9.81 meters over second squared. We got that theta, and I did the calculations prior, is equals to 38.2 degrees. And that's the banking angle that we were looking for.